Okay, so let's get started. So it's probably the biggest thrill of my life to introduce, my own thesis advisor, Professor J. Strother, and it's an incredible story. Someday I hope he'll write about it. I think he grew up in Oklahoma. He was a National Merit Scholar. He probably got to meet the president when you didn't meet the president, but then he did an undergraduate at MIT, decided to come over to Edinburgh to do his PhD. There he actually was part of probably one of the greatest assembly of minds in computer science. Mike Gordon was there at that time as well, and Alan Bundy, Bernie Meltzer, Donald Mickey, Gordon Plotkin, Robin Milner, just a huge group. And so there they actually started developing, what came to be known as the Boyer-Moore theorem prover. They did, actually he met Boyer out there. That was a huge event, and that was a lifelong partnership between Boyer and Moore. In fact, they used to be regarded as one person. The mail would arrive for Boyer and with the middle initial Moore. So the partnership actually started in Edinburgh. They were both American, but they met there. And then they shifted their base to California, actually. Initially at, Jay was at Xerox PARC, and then they were both at SRI. And apparently the way they used to work is they used to actually sit in their respective homes, and they had arranged it so that they shared a screen, and they wore headphones and talked to each other on the phone and typed on a screen that they shared, an Emacs that was common.
Emacs.
It wasn't an Emacs, yeah, that's right.
This was in the early 70s.
Yeah, and then actually, so I first met them when they came to Texas in 1981, and a bunch of us were their actually first batch of students that they graduated. Again, it was an amazing group of students, but working for them was actually just a mind-expanding experience. And the theorem prover that they had, actually, at the point at which they left SRI, and in this, I would say it's the first great theorem prover. Okay, it's literally the first prover that actually proved theorems. And at the point at which they moved from SRI to Texas, they'd done, for example, the fundamental theorem of arithmetic. And at Texas, actually, they had a string of accomplishments. And one of the things they did is actually they decided one day that they would verify the RSA encryption algorithm. That is, the decryption encryption was invertible. And Jay went back home and worked all night. And from when they started thinking about the problem to when he finished the proof, it was 17 hours. So next morning he was still awake. His daughter greets him in the morning, and he tells her that he'd been proving this theorem all night. And Madeline, right?
No, that's Boyer.
Boyer's Lisa, yeah, that's right. Lisa asks him, Dad, have you checked the batteries? So she thought there was something wrong with the theorem prover, that it wasn't.
She was 5.
So long. And so the thing that happened in the 80s actually is that the theorem prover slowly became ready for industrial use, and through the 90s it actually got to be used in an industrial way. And again, this is a theorem prover now that is just robustly usable on industrial projects, and there's a company in Austin called Centaur that makes use of it routinely, on a daily basis. So Jay is going to tell us all about it. Thank you, Jay.
Thank you. Let's see, I can correct that story a little bit. I was actually born in Oklahoma, but raised in Texas. And my parents were residents of Texas, but I happened by circumstances to be born in Oklahoma. And furthermore, Boyer was also from Texas. And so it was really quite odd, because we had both been at MIT at the same time, he as a postdoc and me as an undergrad, but we didn't know each other. We'd both been in Texas at the same time as high school students, but many miles apart. And we didn't meet until Edinburgh. And we shared an office because I was there a year before Boyer showed up, and I kept my office warm by Scottish standards. And so they put Boyer in there with me. Anyhow, okay, yeah, no, I'll tell a little bit about the sort of prehistory of this theorem prover tomorrow, but today I want to kind of talk mainly about applications, because in a certain sense, while my work is focused on building a theorem prover and using it, the thing that other people are more interested in is the applications of that. So this whole 6-week program is mainly devoted to what I consider conventional mathematics via mechanized proof. And by conventional, I don't mean to be pejorative. I just mean to say it's the mathematics that mathematicians have been working on for a very, very long time. But we are in a kind of new era. I regard formal logic as kind of a solution in search of a problem, in the sense that when Frege and the others started formalizing it centuries ago, while they captured the idea of reason, there wasn't what I considered a natural application, because so much of the world is continuous and messy, and logic was almost too discrete, with a few exceptions. Furthermore, formal proofs are almost impossible to construct by hand and believe the result, because the rules are complicated. If you screw up and allow capture or something like that, your proof means nothing. And so as I said, it was a cumbersome solution in search of a practical problem until the invention of the digital computer. Now, when the computer came along, two great things happened for those of us in logic. One was, there was suddenly an application for which we were the natural fit, because digital artifacts are formal systems themselves. And secondly, computers allowed the construction of trustworthy proofs, often under the guidance of a person, but nevertheless, you could trust the proof, and you could construct bigger proofs than you could by hand. And this is a really young development in the history of math. I mean, the history of math goes back hundreds or thousands of years if you go back all the way to Greece and the Indians and the Arabs. But even formalized math is, centuries old. And yet this stuff only goes back, maybe to the late 30s in the sense of Turing's thinking about these kinds of problems, Gödel's thinking. So the interesting thing about this application area is that the theorems that we focus on matter to virtually everybody, whether they know it or not. If you own a mobile phone, if you ride in a car, if you fly in an airplane, if you visit the hospital or the doctor, if you use, online banking, if you don't want to be blown up by some accidental nuclear, what can I say? I'm not worried about intentional nuclear disasters now, but one could at least worry about accidental exchanges, and all of that depends on the computational resources that are, within the scope of this project. That's it. So the way I see mathematics and formal methods is, this is sort of conventional mathematics. It's a well-studied field. You have to be absolutely brilliant to make a contribution, and finding a jewel, hidden in that beach Yeah, and see, I see science as discovery, as exploration. And the whole idea is to walk along the beach looking for interesting things, or beat your way through the jungle looking for interesting things. And to me, that's not an appealing picture. This is the computer science beach, as it were. It's not exactly untrod, but it's pretty, it hasn't been explored nearly as thoroughly. And so even ordinary people can find interesting things, okay? And by ordinary people, I mean just, you know, like programmers can invent algorithms that no one ever thought of that are really, really interesting. So that's what we're on about. Now, this isn't a new idea. Turing explored it. He wrote a paper checking a large routine. His large routine was a factorial program that had an inner loop that did multiplication by addition. So it's two loops. And he wrote a paper that basically was a precursor to the Floyd approach of attaching assertions to code and then checking each assertion. 12 years later, McCarthy wrote that instead of debugging a program, one should prove that it meets its specification, and this proof should be checked by a computer. That's got several interesting ideas. Programs can be specified. Programs can be proved to meet their specs, and proofs can be checked. He kind of was the first, I think, to really put that all together. So we can formalize the semantics of hardware and software. We can prove properties of those formal models. We can check or even discover those properties mechanically. And now we ask the question, but can we really? And that's what this talk is about. Now, the theorem prover that Matt Kaufman and I have developed, and it's a successor to a theorem prover that Boyer and I developed, is called ACL2. It stands for a computational logic for applicative common Lisp. And the basic idea is here. You take a functional programming language, you axiomatize it, you build a theorem prover for that, and then you use it to model other computational artifacts and prove theorems. By the way, that's the home page of the theorem prover. And if I can just go over here. That's the home page of the theorem prover. And you can look it up and you can find the source code and documentation. There's a lot of documentation. There's an online manual that, you type in a topic like def thumb, which is the way you challenge the theorem prover to prove a theorem. You get documentation. It's all hypertext linked. But anyway, meanwhile, I want to demonstrate the theorem prover just briefly first. So here I am this is an Emacs buffer. It's running ACL2. ACL2 presents itself as a read eval print loop. So you type something, it reads it, provided it's well formed, it evaluates it and prints the answer and then prompts you for another. And I have a little script behind the scenes here on the Emacs macro so that I can type a command like that you can't see that brings up the next form. And so here's the form that says 2 plus 3, and it evaluates to 5. And so right away you see that ACL2 is Lisp. It's got the prefix syntax of Lisp. Cons is the way you construct an ordered pair, so I'm conting the symbol Monday onto the list obtained by conting the symbol Tuesday, etc. onto nil. And when I evaluate that, I get what prints as a list Monday, Tuesday, Wednesday. I'm going to include a book. A book in ACL2 is a file of verified definitions and theorems. And this is a model of a very simple programming language. It's actually Turing complete, and we proved that with ACL2. But more interestingly, it's sort of a tiny bit of the JVM, the Java Virtual Machine. So here, ACL2 is reaching into its library and bringing in a book and adding to the set of definitions and theorems. And now I step over into a world where when I type a symbol, it's understood with respect to that package of symbols in one. We won't go into that. And now I have this model of the Java Virtual Machine, a tiny subset, a toy subset. But I'm not going to exploit it right now. I'm just going to, I'll define the function square. Okay, so that says define SQ with one argument x to be x times x. Whenever you define a function, ACL2 has to prove there exists a function that satisfies the equation. In this case, the equation is square of x equals x times x. It's trivial to do that because it's not a recursive function, but functions that recur might not exist. Every function in ACL2 has to talk about that more later. Anyway, I can evaluate square. Square of 7 is 49. Here I'm defining the function exponentiation of two naturals. So I have I and j. If j is 0, return 1. Otherwise, multiply I times the power of I to the j minus 1. And again, here, ACL2 had to prove that that function terminates, and it does so by arguing that one of its arguments decreases on the well-founded domain, the ordinals of epsilon naught. And it also noticed that it always returns a number. And I can evaluate that. 2 to the 5th is 32. And now here's the way you present a theorem to a conjecture to ACL2. I'd like to prove that if I, j, and k are naturals, then I to the j plus k is the product of I to the j times I to the k. And since exponentiation is recursive, this is going to be an inductive proof. I'm going to hit return, and it's going to spew out a lot of stuff. It says at the end the proof succeeded. Just briefly, I'll show you what it spewed out. First thing it did was simplify the function nat is defined to be integer greater than or equal to 0. So it simplified those 3 nats to those 6 hypotheses there. It didn't do anything to the conclusion. Then it decided to try induction. It analyzed the recursion that is evident here and decided it could induct either on j or k. Doesn't think about inducting on I. It chose an induction. It got a bunch of cases.
Why doesn't it think about I?
Nobody is really recursing on I. Think about exponentiation. It holds I constant and constantly decrements its second argument. And what you want in induction is an induction hypothesis like that one up there that will catch the term you get when you start expanding the functions in the conclusion.
So it looks at the occurrences.
That's the kind of inductive analysis it does. Actually, it does it when the function is defined. Anyway, it got a bunch of formulas and proved each of them by simplification. And that was that. And thus ends the first one. Now, a few bullets that I've kind of exposed already. ACL2 is common Lisp. I didn't design it. I just opened the book, common Lisp. It's an ANSI standard programming language. The syntax is Lisp. The data types we support are not the full range of data types. For example, we don't support the floating point numbers. We don't support other things. It's an implicative subset of common Lisp, a functional subset. So we support integers, rationals, characters, strings, lists, and trees, which are both ordered pairs. It's a first order logic. That's really strange for here because most of the logics we hear about are high order. It's an untyped syntax. That's also really strange. But again, that's common Lisp. It's untyped. You can apply a function to anything and something happens. It allows induction up to epsilon naught, which is a stack of omegas. It's got a conservative principle of induction, so when you define a function, if it's admitted, we know the logic is just as sound as it was, and we know that any formula that could be proved that doesn't involve that definition could be proved without that definition. Recursive definitions have to be proved totals. All formulas are implicitly universally quantified. We don't have explicit quantification, so you can't write for all x there exists y. We do provide some support for a type-like discipline. It's kind of similar to PBS's type conditions. We support quantification via something kind of like Hilbert's epsilon, but in any case, I won't go into it. We support the reals via non-standard analysis in a modified version of ACL2 called ACL2R. We support some second-order reasoning via a derived rule of functional instantiation, which says if you prove a theorem about a function symbol, and then there's some other function that satisfies all the axioms about that function symbol, then the theorem that we proved about that one holds for this one. So you can add an undefined function and prove theorems about it in connection with other functions, and then instantiate those theorems. We allow the user to define new equivalence relations. We do rewriting with respect to congruence. And this is really important. I won't talk about it much, but because this is Lisp, it's not hard to define a new theorem prover in the logic as a Lisp function. And then if you prove that that theorem prover is sound, then ACL2 will begin to use it as one of the proof techniques. And that's used a lot by our industrial users. I mean, there are over 150 examples of verified metafunctions in the distributed collection of theorems and definitions. And we'll explore more about ACL2 tomorrow. Now, moving on to what industry is typically doing, we're going to look at a simple programming language, that M1 language. And the idea in formalizing a simple machine, one way is to define an operational semantics on states. So let a state be a four-tuple that's got a program counter, a list of registers, a stack, and a program. And so the program counter, PC, points, it's just a number that indicates which instruction is next in the program. An instruction is an opcode and some arguments. The function step takes an instruction and a state and returns a new state. And the function M1 just takes a natural number n and a state and bangs away at the state n times and returns the resulting state. This is really trivial, simple model. It's easy to understand.
Sorry, what does M1 do?
Pardon?
Again, what M1 does.
M1 is a recursive function that says if n is 0, then return state, else apply step to the state and current instruction.
The current instruction.
And then
Yes.
hit it again with n minus 1. So I'm going to demonstrate a few proofs about this. I want to stress that this is just one way to attack properties of a programming language. There are many, like inductive assertions and or logic and others. And we could formalize those in ACL2, and many people have. And they use various ones, and there are even packages that allow you to reason one way about a program and then prove the theorems from another perspective so you can connect them. But I'm doing it this way because it's easy to get straight into the core problems. All the core problems are the same. So let me go back over here. Oops, I'm learning how to do that. So I'm back in that same ACL2, and I'm defining a constant, def constant. And the constant is a program in this little language I'm making up. And I'll just read it briefly. iLoad1 takes the contents of register 1 and pushes it on the stack. If EQ pops the stack, and if the top of the stack was 0, it jumps to the, in this case, 10, the argument to FEQ, plus the current PC, so it jumps 10 down, so it would jump to 11 here. imul pops two things off the stack, multiplies them together, and pushes the result. iStore pops the stack into the register indicated, and so on. So this is just a program to compute factorial. Is it factorial or is it it's exponentiation? So what it's doing is if j is 0, it jumps to the end and pushes the final answer, which is held in register 2, and halts. Otherwise, those 4 instructions, the load 0, the load 2, the imul, and the store is the same as I times k is assigned to k. These next 4 is the same as j gets j minus 1, and then you go to minus 10, which is back up. This is 10, so that means go to absolute location 0. I'll go back to the top of the loop. Yeah, I could use that. So I'll define that. That's just a list. I can say, what's the length of that? You know, it's 13. I mean, it's just an ordinary list. Now I'm defining a function to make it easy to build a state. This function takes I, j, and k, which are the contents of registers that I want, and it makes a new state with program counter 0. The registers are I, j, and k, the stack is empty, and the program is that fixed one. So now I can build states. So like I can say, make me a state with register values 11, 12, and 13. And I get this object. So that first thing up there is the program counter, then the values of the registers, the stack, and the program. And I can run it. So I can say, for example, build a state with that's poised to execute 2 to the 5th, then run it 1,000 steps. That's just a made up number. Take the stack of that final state and show me the top. And it says 32. And I can say, well, what's 2 to the 64? And it says that. And I can ask, what's 2 to the 64 according to that other function we computed? And it says that. So they happen to be the same, but they're computed 2 different ways. This answer was computed by our little program, being interpreted by M1. This was computed by the recursive function that is sort of the piano definition of exponentiation. Now the question is, I don't like this random big number here. So why don't I define a function that computes how long it takes this program to reach halt from the beginning? Now you can't always do that. That's the termination problem, but you can do it often. And we have code that does it for given situations. In any case, this function is called a clock function. It takes the arguments of the program. If j is 0, it takes 3 steps to reach the halt. The iLoad, the FEQ, and the iLoad down here at the bottom. 1, 2, 3, and then you're at the halt. Otherwise, you add 11 to the result of running the same function on j minus 1. So it's not a deep function at all. But anyway, so I defined that. And now I can say, like, well, how many steps did it take to compute 2 to the 5th? And the answer is 58. And I can say, well, how many steps does it take to compute 2 to the 1,000? And the answer is 11,003. And I might actually ask the machine to compute 2 to the 1,000. And so what you're about to see is how long it takes to run 11,000 steps of this machine. Let's put this on the top. So here goes. Okay? It took almost no time. ACL2 is very fast, and that's 2 to the 1,000. I'll talk more about speed later, but it's really paramount. So here's the theorem about that program. It says that if I, J, and K are natural numbers, and I build a state poised to execute that program on I, J, and K, and I give it the clock for I, J, and K, then the result is going to be a state with program counter 12, which happens to be pointing at the halt state. I get a final list of registers that I is unchanged, but J has been decremented down to 0. And in this location, I find K times I to the J. Also, I find K times I to the J on top of the stack, and the program hasn't changed. I could write a program that changed, but I have to add some new instructions to modify that fourth component of the state, which we do on some of our models. But anyway, so let's ask ACL2 to prove this. Okay, so again, I won't show you the proof, but it did an induction and it unwound, and it took it 0.04 of a second, and now we know that that code has that property, and we can prove a simple corollary. And let me show you what that corollary actually said. Here's that corollary again. What it says is if I, J, and K are natural numbers, and fin state is the final state by running M1 on the initial state, that number of clock ticks, then the final state is halted, and furthermore, the top of the stack contains K, it contains that. This is the kind of theorem that people like to see because it kind of ignores the parts of the state you're not interested in. But the first theorem I proved is the one you have to prove inductively, because if you try to prove this inductively, you don't know enough about this not strong enough to go through induction. I mean, it doesn't even say, for example, that the program component of the state is still the program I was reading. Anyway.
So it's important there to have K as a variable.
Yes, K has to be a variable here. If you tried to prove this theorem, with K being initialized to 1, then it wouldn't go through because, again, it's not strong enough to go through induction. You need a general theorem. If K is being modified in the recursion, then the first theorem you want to prove about that function is what happens in the general case. We'll play with that tomorrow. So I'm going to kill that. Now I want to show you one other aspect of this kind of modeling that is actually quite useful. This is not a theorem. But really what I'm saying is what happens if you build a state poised to execute our little program on I, J, and K, and you run it 11 steps. I want to prove that it's equal to XXX, which of course it's not. So this proof is going to fail. But what's interesting is when it fails, I get to see a symbolic representation of the state 11 from here. So let's look at that last goal. See, it's now trying to prove that XXX is equal to the state with program counter 0, but I is still I. This variable has been decremented by 1, and that variable has been multiplied by I, and the stack is still empty. So that's an interesting way to kind of explore what this program does by putting the program counter at a place and then executing some number of steps and looking at the result. And that's actually used to reverse engineer code that you have a semantics for the machine, but you don't know what the program is doing. In any case, okay, that's the end of that. And now the problem is still, okay, well that's good, that's a toy language and we proved some toy theorems. Can we scale it up? So what started, and Shankar alluded to this, is in 1994, which was a long time after we were doing this kind of stuff, I proved that theorem that you just saw in 1978 with mechanical theorem prover. So that's not a new thing at all. But we kept working on the prover and engineering it so that it could handle bigger formulas. But anyway, we saw this in the New York Times in November of '94. An elusive circuitry error is causing a chip used in millions of computers to generate inaccurate results. And a few months later, Intel took a $500 million write-off to cover the cost of buying back all the Pentium 1s so that it could replace them with chips that could divide. Meanwhile, there was a floating point standard, and the floating point standard says that elementary operations are to be performed as though you did the mathematically precise division in this case, and then rounded the result to the indicated precision. So the IEEE defines some rounding modes like truncate to 32 bits, or round up to the nearest, or whatever, various rounding modes. And so the elementary operations are all specified to be the standard mathematical operation, so in quote, infinitely precise P divided by Q, and then round. But of course you don't compute it that way. Now, at the same time that Intel was losing $500 million, AMD asked me to verify their floating point algorithm for the K5, which was the microprocessor that would compete with the Pentium 1 from AMD's side. This was the pseudocode for it. It's just 32 instructions. Each one of these instructions could be taken to mean take this floating point number, add it to that floating point number. No, let me back up. Take the rational denoted by this floating point number, add it with mathematical precision to that rational, put it in that thing, and then round it according to the sticky rounding mode to 17 bits of exponent and 64 bits of precision. So over here you see IEEE rounding modes and AMD rounding modes. And on this side you see just clear mathematical operations. And that's the pseudocode they wanted to implement. They wanted to implement that because they had been testing this device for years before tape out. The tape out means producing the mask that they'll produce the chips from. But in that same fall that Intel discovered they had a bug, the AMD managers decided that floating point was not important to modern chips. In particular,
That's okay, it goes off.
okay. So a chip is a rectangle, and over here is an area devoted to like the memory, and over here is an area devoted to the ALU, and over here is an area devoted to the floating point unit, and there are some registers, and so on. And then each team of tens or sometimes hundreds of designers is saying, okay, you have this many square millimeters to implement something. And you guys in the ALU group have this many square millimeters, and so on. So that floating point team had been working on that, testing it, and so on. And then in that fall, when Intel made their discovery of a bug, coincidentally, AMD decided that they didn't need as much functionality here, and these guys needed a lot more. And so they just cut the area of the floating point team and gave it to the memory team. And that meant that the floating point people, at the last minute, had to throw away a lot of circuits they had designed and implement things like floating point division in terms of stuff they could preserve here, like floating point multiplication and subtraction, with no time to test. At the same moment that Intel had just lost $500 million, okay? There was a really wonderful opportunity.
So that was microcoder.
Yeah, so Floating point division on the K5 was microcoded for that reason.
Whereas Intel's was SRT.
Intel, yes, but the algorithm's the algorithm. And everybody uses different algorithms. And this algorithm is a roll your own floating point division algorithm based on the functionality that was left on the chip after they threw away a third of it. So roughly speaking, this is how the AMD algorithm divided 12 into 430. It first magically computed the reciprocal of 12, 1 over 12, but it doesn't get it completely accurate. It just gets a floating point approximation of 0.083. And then, because we have a multiplier still on this chip, we can multiply 0.083 times 430, and we get roughly speaking, the number times 12 goes into it, and that's 36. So you write down 36 as the first quotient digit, you compute the remainder, which in this case is -2, and you iterate. And AMD figured out that it was sufficient to iterate 4 times. And then you add up all those quotient digits and you round the result and you get the right answer. Or do you? Now, first of all, how do you compute the reciprocal? Then you just use Newton-Raphson. So and by the way, to use Newton-Raphson, you have to take that initial guess at the reciprocal. And that's done by looking at a table that says if the top 8 bits of the divisor is this, then use that as the initial approximation of the divisor of the reciprocal. Going back here, when you look at this, you can see that the first 5 instructions, 6 instructions is iteratively computing the Newton-Raphson approximation to the reciprocal, and then you start doing the computation of the quotient digits. In any case, so the question is, if AMD built this, would it work? A bug could cost them hundreds of millions of dollars. And on the fastest machine that exists today, which is the Taihu Light machine in China, which operates at 93 petaflops, that's 93 times 2 to the 50 operations per second. Testing all the possible cases for a floating point divider takes this many years, okay? So that's the challenge. That's why testing doesn't work very well in this domain.
Can you explain something here? When you say cases, you mean ways the conditionals could go, or individual floating point inputs?
Test every floating point input. Okay. Test every floating point input of a 64-bit wide, 64, okay, with all the rounding. So here's the theorem that Matt Kaufman and I proposed to AMD. If P and D are floating point numbers in the appropriate input format, and D is non-zero, and mode is an IEEE rounding mode, then the function that represents the microcode is equal to the absolutely precise P divided by D rounded according to mode. Now that's the IEEE spec for division in this case. And here's that theorem written in ACL2. And we set to work proving it, and we needed lemmas. We didn't have any about floating point. We proved 1,200 lemmas about floating point. The first one up there, for example, says that if you truncate x at I digits, and then you truncate it at j digits, that's the same as truncating it at I if j is bigger than I. And so on down. But there's a bunch of lemmas like that, and we proved them.
You have 15 minutes.
Okay. That library of floating point lemmas was then used to prove the algorithm correct. The entire project, from signing the non-disclosure agreement to the QED, took 9 weeks. The proofs were completed before the device was fabricated, and 9 weeks is less than this. So this was a big win, and the library was used for a long time. In '97, AMD built software to translate their in-house hardware design language to ACL2. They used the tool to generate ACL2 functions to model the floating point on their next chip, the Athlon. They tested it by running the ACL2 on the same suite of 100 million floating point test vectors to see if it did the same thing as their simulator, which heretofore was the only semantics they had. And so here you see the need for speed, because we're talking about running a logical model on 100 million examples. Then they proved that the ACL2 functions were compliant with the standard, and they found and fixed 3 design errors that had not been detected in the 100 million tests.
How many did they detect on the tests?
None, because their design had already passed all their tests. But there were still 3 lurking bugs that were found by proof.
So what kind of errors are those?
I don't actually know. I didn't do this work. One was a sign error, which is really egregious. They returned the answer with the wrong sign. Early uses of ACL2, this spurred a lot of other companies, Motorola, AMD, Rockwell Collins, IBM, and Sun, all started looking at this thing. And then in 2007, Centaur, which builds x86 microprocessors in Austin, challenged us to prove their floating point addition correct. And these devices are very complicated. This gives you an idea. The floating point addition unit of the Centaur VIA microprocessor handles single, double, and extended precision, so up to 80 bits. It's pipelined to deliver 4 results every clock cycle. It's 33,000 lines of code written in a hardware design language called Verilog. It takes as input over 1,000 pins that tell you what you're supposed to do. And that includes 26 different clocks. Each part of the unit is clocked at slightly different rates depending. And it outputs 374 signals. So they challenged us to do that. It took about a year to build the infrastructure to make that happen. And a bug was discovered on exactly 1 pair of inputs. So that's really interesting. This bug is 1 case out of 2 to the 160. It would have been a very hard bug to stumble upon accidentally. Today, ACL2 is an integral part of Centaur. The Centaur design team consists of 3 full-time employees and a couple of interns. They build, they're the 3rd largest provider of x86 microprocessors after AMD and Intel. They have an ACL2 spec of their microprocessor. They validate it by running the ACL2 against Intel hardware, AMD hardware, and their own hardware. They translate the entire design into a formal object in a few minutes with a program written in ACL2, and then they validate various parts of it. The interesting thing is this comment here: all proofs are rerun nightly on a cluster of 150 odd machines at Centaur. And so if a designer changes a design and checks it in, then that night any theorem about the old design is attempted about the new design. We call that proof maintenance. You don't often think about proving the same theorem over and over again. Of course, that would be silly. But what happens in this world is that the underlying definitions and models are changing. And so you have to prove the same theorem about a slightly different design. And so bugs introduced today are found tonight and then fixed tomorrow is their slogan. And that has really sped up the development cycle. I won't go on, but Centaur's toolchain is available as part of the ACL2 distributed library, and it's used by other places like Intel and Oracle. So you're beginning to see a kind of community of prover drivers that are all speaking the same language because they're using the same tools. I won't go into this except the Intel note here. Intel used ACL2 to prove some stuff about an elliptic curve crypto chip they're building. One is that 2 to the 255 minus 19 is a prime, and the other is that the corresponding curve is a real. And that was an interesting proof. This is a talk given by the vice president of Oracle in May of this year. And I just want to show that I'm making real the fact that companies are using it, because here you're seeing the words of a vice president. The improvements that using ACL2 actually reduced the lookup tables in some of their floating point by 60% because the guys doing proof noticed things. By the summer of 2015, they were working on latency, so speed up these things. It goes on. They're now doing things like temporal properties and absence of starvation. Oh, there's another note. This is important. This is the vice president of Oracle telling us that they don't need extensive testing on some of the parts they verify now because they're beginning to trust this tool. Rockwell Collins uses it. They build crypto processors as well as avionics devices. And an interesting thing there is the information flow proofs in the second bullet. On the basis of a formal proof done by Rockwell with ACL2, the National Security Agency accredited their chip to have MILS, multi-level security authorization. So 2 processes could run on the chip with confidence that one of them could not transfer information to another. We have an x86 model at UT Austin. The x86, the manual for the x86 from Intel is 3,000 pages. This is just, you know, my little M1 state had 4 components. This is a very abstract view of the x86 state with memory tables and lists of slide buffers and other things. Our model of it can run binary. So you can take a C program, compile it with GCC, get some binaries, load it into the ACL2 model and run it. It runs at about 3 million instructions per second. The little M1 model I showed you was running at 300,000 instructions per second. So this model is optimized for speed, but they've also done some proofs with it. ACL2 got here because Matt and I really pay attention to industry. So these are the changes to ACL2 that were requested by Centaur alone, just Centaur, since Centaur started in 2009. And you can see where it's not like we're working in a vacuum. Our users are constantly saying we need this and that. The main thing they want is faster execution speed of the logic. They build models, they want to use those models as prototypes, and they want the logic to execute even faster than it does. They want more automation in their proofs, especially in limit discovery and definition discovery. They want better ways to view large formulas. For example, we've seen formulas like, just roughly, you might prove that an operating system has some property given the hardware it runs on. That sort of P implies Q, where P is the hardware and Q is the operating system, sort of. Now start expanding that simple formula. The operating system, of course, takes hundreds of pages to describe. The hardware takes hundreds in all of the cases. And pretty soon we deal with formulas that are gigabytes big. So to print the formula takes a gigabyte of text, okay? The user doesn't want to look at a gigabyte of text. So how do you view large formulas? You don't think about that problem, but our users do. And right now, the best we can offer them is Emacs. Scripting capabilities, they're connecting ACL2 to all kinds of other tools, and they wish they could do it all in ACL2. And they wish to build GUIs, graphical user interfaces, because the group at Centaur, the three that use ACL2 and keep the regression suite running, and tell the engineers what went wrong every morning. Those engineers, when they check in the system, certain checks are done automatically, and they get email reports and GUIs that let them look at things. And that's done in ACL2 to the extent it can be, but then they have to use connections to other programming languages to display the results and stuff, and they would like not to do that. An interesting thing our users don't ask for are quantifiers, higher order functions, and strong typing. It's not that they don't want that, they'd love that if they had it. But what they want is faster execution speed and better reasoning. Okay, and they don't ask about this because they're focused on the other. I want to finish by just saying that the general challenges here, what is the spec? What are you supposed to prove? It took us 9 weeks to write down and prove the formula about the AMD divider. It took us 2 months to convince the AMD management that that formula was the one they should care about. Okay. Now that we have standard models of floating point, that's less a problem. But anyway, what does security mean? Everybody wants to prove it, nobody knows what it means. Can we make concurrency tractable? Oh, everybody works on concurrency and there's been some great work, but it's still a pretty hard problem. Can you virtualize a modern computing device? Everybody thinks about modern computing devices as being virtualized. That is to say, you can run in a sandbox, as it were, and not pollute your real hardware, while believing that you have access to the entire machine there in your little sandbox. Can you do that? Well, it hasn't been done yet accurately. And
So
designers
the
are
Greenhill's integrity proof it doesn't do that?
they don't pretend to provide the entire hardware resources. I mean, that's the problem. Is you'd really like to virtualize the x86 where you can look at the page tables. They only let you look at pieces. Designers are faced with a lot of problems besides functional correctness, like timing and power use and other things. How can formal methods contribute there? Because all of this stuff is digital artifacts, all of these are mathematical questions, and we ignore them at our peril. And furthermore, trying to define concepts and state conjectures is a worthy mathematical task. I would argue as worthy as proving theorems. Just figuring out what it means really clearly, these things is important. Anyway, you know this by the other talks you've heard already. What does mechanical reasoning, not just ACL2, but any system, require of the user? You've got to accept the constraints of the formal logic. You've got to think precisely. You've got to be able to digest new ideas and express them in formal terms. You need good first strategic judgment, and by that I mean you are often in this business creating new theories about concepts that aren't in books. You have to master your own theories and know what you've got. It takes creativity, especially in doing inductive arguments. It takes collaboration, and it takes respect for the other team members. What it doesn't require is accuracy in manipulating formulas, perfect recall of the site conditions for every lemma you know, or a deep understanding of the electronics or the hardware. Anyway, I won't go on, except to just say, in an upcoming talk tomorrow, I think at 1:30 here, I'll give a tutorial on how ACL2 works. So that's it. Sorry, I should hang around and answer questions.
So how do you get the models to execute so quickly? Is everything compiled down to Lisp, or do you?
Yes, ACL2 is Lisp. So when you define a function in ACL2, it's also defined in Lisp.
So at the bottom, you're always running Lisp.
Almost.
Compiled.
Almost. It's
So
not
how do you-
quite true. The reason is that Lisp, for example, take the symbol, the function car, which is alleged to return the first component of an ordered pair. What happens in Common Lisp if you give car 7, a number and not a pair? The manual says an error is caused. And it's non-deterministic. It could log you out, it could erase your file system, it could access contents of memory location 7, who knows? And so there's actually a sense hidden in the Common Lisp spec of a well-typed program, because it says, the standard says, that car shall only be applied to, is expected, the arguments are expected to be pairs. And if not, it's your problem. Okay, something will happen, it's your problem. And so we have this notion of what we call a well-guarded formula, where you don't apply car unless you know the object is applied to its cons. And so what happens when you define a function is 2 functions get defined in Common Lisp. One is literally what you wrote, compiled, etc. And the other is an interpreted model that will throw a polite error if you apply car to a non-cons. And then, if you prove the theorems that establish that your original function respects the type decision, then we'll run that one. And if you don't prove that theorem, we run the slower one. And the slower one is about 10 times slower than the fast. And so the x86 model that's running at 3 million instructions per second has been proved to be what you would think of as type safe. Prove that every function in it is applied to something of the right shape. But we don't have typed syntax. We allow you to attach a predicate that and type checking is done by proof.
So speaking as a former Lisp compiler writer, I was interested in your comment on the need for speed. Have you had any pressure from your customers to move on to other programming languages where people are throwing more resources at making their compilers faster than is available in the Lisp world?
Not yet. Part of it is that this theorem prover is 45 years old, starting from the Edinburgh theorem prover, which was also for pure Lisp. And so if you wanted to adopt another functional programming language, somebody would have to write a theorem prover. And it's
I think he meant another target language.
Target language, write your theorem prover in another target language so that you get the
Or,
benefits of the better
or execute.
optimizers in other languages.
Well, no, we haven't thought about that. But do understand that it's not the speed of the theorem prover that matters, it's the speed of the execution of the programs the user has defined that matter. But you're suggesting that we could perhaps translate those Lisp programs into some other system that has a better compiler. Do you know such a system?
No, I'm just aware that the Common Lisp community is shrinking and the amount of effort that Lisp implementers have available to do some of the fancy optimizations is very limited, whereas other more fashionable languages, of course, have
Right.
bigger compiler writing.
Right, and
tools.
that's, by the way, there are currently 7 Common Lisps that are maintained by independent groups. And our code is written in Common Lisp and is a subset of all of those. And we tested on all of those Common Lisps. And we have special relations with a couple of Common Lisp development teams, and we pay them to improve the compiler. But you're absolutely right. Gary Byers has dropped out, and so he's not maintaining the CCL compiler anymore. And they haven't got somebody to do it. And so it is a worry. And you're right that a programming language with a larger user community and maybe more commercial interest would help. We haven't looked at it. I'm retired, man, I'm not gonna build another.
Me too.
What's your name?
I'm Andrew Watts. I used to work with LispWorks, which is the
Oh,
public Lisp
Yeah,
company here in Cambridge. I don't know if you target them.
yeah, we've run on this.
Any other questions?
Thanks very much.
Okay.